comes in the denominator, it means V by Q is equal to 1 by C1 plus 1 by C2 plus 1 by C3. But what is V by Q? V by Q is basically 1 by C, because we know the relation Q equals CV. So V by Q is 1 by C. So finally we have an equation, three capacitors in series, that 1 by C is equal to 1 by C1 plus 1 by C2 plus 1 by C3. So this is the equation if we are putting three capacitors in series. So 1 by C will be equal to 1 by C1 plus 1 by C2 plus 1 by C3. If we are putting the fourth capacitor in series with it, then it will have 1 by C1 plus 1 by C2 plus 1 by C3 plus 1 by C4. It means if the capacitors will be increased, then this line will also be increased. Okay, now capacitors in parallel. We have seen the equation of capacitor in series. Now what happens if we put the capacitors in parallel? In DC circuit we have seen that resistance, if resistance are put in parallel, then the voltage will be equal but the current will be divided. So if we are putting capacitors in parallel, then the voltage between each capacitor will be same, but the accumulated charge on each capacitor will be different. Here we are having three capacitors, C1, C2 and C3 farads, respectively connected in parallel, so that the charge accumulated on first capacitor will be Q1, the charge accumulated on second capacitor will be Q2, and the charge accumulated on third capacitor will be Q3, and the voltage of each capacitor will be equal, that is V. So now we are going to have the formula. Here we can say that voltage V exists across all the three capacitors C1, C2 and C3. Q1, Q2 and Q3 are the charges across C1, C2 and C3. So different charges will be accumulated on different capacitors. Here comes the equation. Q is equal to Q1 plus Q2 plus Q3. It means the total accumulated charge is equal to the charge accumulated on first capacitor plus the charge accumulated on second capacitor plus the charge accumulated on third capacitor. So the charge accumulated on first capacitor is Q1, the charge accumulated on second capacitor is Q2 and the charge accumulated on third capacitor is Q3. So we can write that Q is equal to Q1 plus Q2 plus Q3. But what is Q? Q is CV. We have derived the equation, so that we can write that Q is equal to C1 into V, which is Q1. In place of Q1 we can write C1 into V, where C1 is the capacitance of first capacitor and V is the voltage across it, plus C2 into V, where C2 is the capacitance of the second capacitor and V is the voltage of that capacitor, plus C3 into V. It means C3 is the capacitance of the third capacitor and V is the voltage across the third capacitor, so that we can write Q is equal to C1 into V plus C2 into V plus C3 into V. Now if we take V as common, so that we can find that Q is equal to V in bracket C1 plus C2 plus C3, and after that if we take V in denominator, then we have an equation Q by V is equal to C1 plus C2 plus C3. And finally, what is Q by V? So Q by V is basically C, and that is capacitance, and that will be the equivalent capacitance. So C is equal to C1 plus C2 plus C3. So if we are taking capacitors in parallel in this arrangement, we can find that C, the total capacitance, is equal to C1 plus C2 plus C3. It means the total equivalent capacitance is the capacitance of first capacitor plus the capacitance of second capacitor plus the capacitance of third capacitor. And here the Q is accumulated charge, V is the voltage and C is equivalent capacitance. Now we are going to see an interesting thing, that is energy stored in capacitor. How much energy it stores? It has an equation and we are going to derive that. So when a capacitor is charged, the voltage source has to spend some energy. This energy is stored in the electrostatic field, and after that we can use this energy in our application. This energy comes if the charge is transferring from one plate to another plate, and we have seen that the potential difference is created, and this is the energy which is stored in the capacitor. So how much energy is stored in the capacitor? We have an equation. Suppose the capacitance of a capacitor is C farads. Potential difference across the plates increased from V to V plus dV volts in dt seconds, and the charge supplied is dq coulombs. So we can write that dq is equal to C into dV, where dq is the change of charge and dV is the change of voltage. We know that q is equal to CV, so that we can write that dq is equal to C into dV. After that, the second equation is dq is equal to I into dt. We have learned before that q is equal to I into t. It means that the charge is equal to current into time. So that here dq is the change of charge and dt is the change of time. So that we can write that dq is equal to I into dt, where I can be known as charging current. After comparing both the equations, we can write that I into dt is equal to C into dV, because we are comparing dq. So C dV will be equal to I into dt, and after that, making I the subject, we have the equation I is equal to C into dV by dt. Now we have to find the instantaneous value of power of the capacitor. So the equation of power is simply current into voltage, that is P is equal to VI. So the instantaneous value of power is equal to the instantaneous value of current and into the instantaneous value of voltage. So it will be VI into watts. So the unit of power is watts. Now putting the equation C into dV by dt in place of I, so we can write that V into C dV by dt. The power is equal to V into C dV by dt. Now comes energy. We have seen that the power is equal to C into dV by dt. Now what is energy? So energy is basically power into time. So we have taken time as dt. So if we take V into C dV by dt into time dt, so we will finally find that the energy stored in a capacitor is CV dV joules. The energy is measured in joules. So it is CV into dV. Now if the potential difference across the capacitor is increased from V0 to V volts, it means we are having integration from 0 to V volts, CV into dV. And after that we find that the integration comes as C into V square by 2. So that is the total energy stored in the capacitor. We have a formula. The energy stored in a capacitor is half CV square. And if you put the value of V as Q by C, then you will find that the energy stored in a capacitor is Q square by 2C. So sometimes in example we use the equation half CV square, and sometimes if voltage is not given and if charge is given, then we can find the energy stored in a capacitor as Q square by 2C, where Q is the charge accumulated and C is the capacitance of the capacitor. Now we have a beautiful example on this theory. We can use capacitors series example in this. See the example. Here given the three capacitors are given in series: 10 microfarads, 20 microfarads and 40 microfarads. The values of these capacitance are 10, 20 and 40, and they all are connected in series, and the voltage 400 volt is given. Now what we have to find? We have to find the total capacitance of the circuit. It means C, the total charge in circuit, which is Q, and the total energy stored in the capacitor, which is E. This example is very important and it is frequently asked in exams. Here we have an arrangement: C1, C2 and C3. Three capacitors are arranged in series, and the value of C1 is 10 microfarads, the value of C2 is 20 microfarads, and the value of C3 is 40 microfarads, and the voltage is 400 volt. Now we have an equation for capacitors in series. We derived the equation for capacitors in series as 1 by C is equal to 1 by C1 plus 1 by C2 plus 1 by C3. So here we can write 1 by C is equal to 1 by 10 microfarads plus 1 by 20 microfarads plus 1 by 40 microfarads. After concluding that, we can say that C equivalent is equal to 10 into 20 into 40 by 10 into 20 plus 20 into 40 plus 10 into 40. It means the total C or equivalent C is equal to C1 into C2 into C3 by C1 into C2 plus C2 into C3 plus C1 into C3. So finally we found the capacitance, the equivalent capacitance as 5.714 microfarads. So our first aim is done, total capacitance of the circuit. Now we will find the total charge in a circuit. The accumulated charge Q is equal to CV. We derived the equation Q is equal to CV. What is C? We found that C is 5.7 microfarads and the voltage is 400 volt. By multiplying both of these, we can find total accumulated charge as 2280 microcoulomb. And finally, the total stored energy. We derived the equation energy stored in capacitor as half CV square. Here we have given the voltage 400 volt, so we cannot use the equation Q square by 2C. It is possible to use the equation, but half CV square will be easy. So half CV square, where C is the capacitance and V is the voltage. And then by multiplying this, we can find that the total energy stored in capacitor is 0.456 joule. Remember all the units of charge, energy and capacitors. Now same, if these three capacitors are connected in parallel, find C, Q and E. So now it is very easy, because if the capacitors are in parallel, we have an equation C equals C1 plus C2 plus C3. So we have C equals 70 microfarads, and after that accumulated charge we can find by Q equals CV, and then energy stored in capacitor as half CV square. So it is 5.6 joule. Then we have types of capacitors. There are many types of capacitors. For example, mica capacitors, which is very excellent dielectric. Mica is very excellent dielectric. It is used for making stable and accurate capacitors, but it is costlier. So it is mainly used for making capacitors used in the high frequency circuits. After that comes ceramic capacitors, in which ceramic is used and it is useful at high temperatures. And then comes electrolytic capacitors, and they can work only with DC supply. So these are the applications of capacitors. I am very thankful to Gujarat Technological University for giving me the golden opportunity. I hope you like the lecture. Thank you so much.